In our previous video, we introduced the idea of magnetic flux. So magnetic flux is integral B dot dA. Okay. We also introduced the idea that we have motional EMF. So the motional EMF is going to be VBL, but we also saw that the motional EMF here was going to be equal to, it's going to be proportionate to the rate of change of the flux. So the rate of change of the flux. Okay, we'll get back to that. So the motional EMF gave us an EMF, was due to the motion, and we realized that's related to the flux. And so Lenz's law says that the direction of the EMF in a circuit is going to be in whichever direction minimizes the change. So you actually saw something like this in lab. So if we had a loop of wire right here, and it's in a magnetic field, so we have a magnetic field that's into the board here, and if I decrease the magnetic field, so the flux in here, the flux is going to be equal to integral B dot dA. So the flux is going to be B times area, so B times pi r squared. If I decrease the magnetic field, we know there's going to be an EMF. The EMF is going to be equal to, is going to be proportionate to the rate of change of the magnetic field. We kind of derived that last time. Okay, so we put a minus in there. The minus is Lenz's law. This entire thing is actually called Faraday's law. Okay, so this is Faraday's law, and it says that the rate of change of the magnetic flux is going to be equal to the EMF. The minus sign says, that's from Lenz's law, that says the direction is going to be whatever direction minimizes the change. So if the magnetic field up here were decreasing, Lenz's law says that the direction of the EMF induced, the direction of the EMF that's going to be induced is going to resist the change. So the magnetic field is decreasing, the flux is decreasing, but if you increase the strength of the magnetic field inside there, then that would lessen the decrease. Well, in order to make the magnetic field inside, by the right-hand rule, in order to make the magnetic field go down like that, you would have to have an EMF this way to induce current flowing around in a clockwise direction. Okay, so on the other hand, if your loop was like that and you increase the magnetic field, that means the magnetic field inside is getting too strong, and so you want to add some magnetic field out of the board to lessen the increase. And you do that by having current go around counterclockwise in here. So if the current goes counterclockwise, that would lessen the increase, because that would make a magnetic field out of the board that would lessen the into the board increase. And so that's the idea of Faraday's law. So it says the direction of the EMF resists the change in the flux. And you kind of discovered that in lab, that when you had the coil of wire and you put the magnetic field, or you put the magnet into the coil wire, it caused the current to flow one direction. When you pulled it out of the coil of wire, it caused the magnetic field to flow in the other, or caused the current rather to flow in the other direction. And so that meant that that was an example right there of Lenz's law in action and Faraday's law. Faraday's law, the rate of change of the magnetic field. The faster you pushed the magnet into the coil or pulled it out of the coil, the bigger the effect. And the bigger the magnetic field. So the stronger the magnet, the bigger the effect. And so those are all examples of Faraday's law and Lenz's law. And so that was the basis of that lab that you did before spring break. And so thankfully we got to get that in before this forced break here, because it's going to be very difficult to actually do labs of that sort, physical labs now. So at least you got to experience it. That's what that whole lab was about, and a lot of y'all were having trouble with that lab because it was primarily an experiential lab, and rather than being very quantitative like some of the other labs. But that's kind of um, that's kind of where we ended up. So now we have an example of Faraday's law, Lenz's law, and those are really the main parts of chapter 30. There's one more part of chapter 30 that is inductors, and we'll talk about that as well, and that gives us RL circuits, which we've talked about in the lab. But this gives us the basic theory. Those other things come out of this. But before we go into inductors, I want to do some example problems of this and show you some more applications.